Okay, so my name is Adrian Otto, and I've come to talk to you about Docker. You are all like lottery winners, apparently, because on sked.org, where we have this session, there were, I think there's 66 seats in the room or something like that, and there were like 524 RSVPs. So like, we had like a small panic attack this morning when we're like, what are we going to do? There's going to be like a flash mob at the door for this Docker workshop. So all of you, thanks for reading your email and coming early. There are prerequisites to participating. I'll get to those in just a sec. This is what we're going to cover. There are a total of 2 lessons and 2 labs and a lecture that kind of talks about the overall like toolbox landscape. There is also a 3rd lesson. So if you're a rock star and you're just going way faster than the rest of us, there's more stuff in the slides that you can go ahead and try. But I'm not going to aim to get that stuff done because I have a whole lot to say and not a whole lot of time. This is only a 90-minute session, and I've got at least 2 hours worth of content here. So lesson 3 is extra credit. So, prerequisites. In order for you to participate in the lab portion of this, you're going to need to have a working OpenStack cloud account. I don't care who the cloud is, but once you create an instance, you must be able to get to it remotely from here. So if it's not assigning public IP addresses or automatically making elastic IPs that front end so that the metadata in the response from the Nova create command needs to be an address that you can reach from here. If not, none of the lab stuff's going to work. Okay. If you have, just a sec, if you have a Rackspace Cloud account, that will work. And the examples that I will show will assume you're using the Rackspace Cloud. If you're not using the Rackspace Cloud, everywhere I have -D Rackspace, you're going to use -D OpenStack. Okay? First question? I doubt you'll get it done in time. So if you don't have a working cloud account, my suggestion is that we swap someone in to take your spot, and you can take a standing room, and you can stay for the lecture part of it, and you can use the slides and do self-study on the lab part of it. But you probably won't be very entertained when we're doing the labs and you can't participate. Okay? Another question here? I'm sorry, I didn't hear it. You need to be able for your laptop to reach the address of the server using the IP address attribute that is in the response from the Nova service. Okay? If that happens for you, then great. However you get that done. But if you've got an OpenStack cloud and it's creating instances that you can't reach from here on a public address, that could be problematic unless you have some way to work around that. Okay. You're going to need the Docker client binary on your laptop. If you don't already have it, I will put a link up for where to get it. You also need the Docker machine client binary, which I also put a link up to. Okay? If you don't have either of those things, again, you can't do the lab. So first, download the slides. This is where the slides are hosted. This is going to be, if you're going to move faster or slower than the group, this is how you're going to continue to go through the lesson. In the Docker machine GitHub repo is where you're going to find a releases tab. It's like near the top in the middle. You go to the releases tab and there are binary releases. You need the binary that runs on whatever kind of machine you brought today. So all you need to do in order to run Docker or Docker machine, the minimum required is that you have the binary. It's built in Go, so the binary itself is statically linked. You don't need anything else. All you need is the binary and to chmod +x that file, and that will allow you to do everything we're doing today. You don't need to download boot to Docker. If you don't know how to install, if you don't know how to install Docker, you can install boot to Docker and it will install the client, but you don't have to use boot to Docker to do this lab. So that's the prerequisites. Questions on the prerequisites? All right, so I'll let you all get those things downloading. I'm going to talk for a solid 15 minutes, so if you don't have this right now, don't panic, that's fine. But by the time I'm done talking about tools, that's when you're going to need this stuff to be working. Okay. Simon, this is my colleague Simon Jakesh. And okay, Andrew Melton is here, and Thomas also here. All of us are here to help you. So if you get stuck, we're only going to be able to access people that are on the perimeter, since the way that we're kind of really tight in here. So if you are really having trouble, ask to switch with someone who's not having trouble, who is accessible to the outside, and one of us will try to get you through whatever you're stuck on. Right. So we'll just do our best there. So if you're struggling, or you know you're going to have trouble, then come to the edges. And if you know you're a pro and you're just here for additional information, maybe go more toward the center. Okay? All right, so let's talk about the container itself. Container technology has been around a long time. It's been in the Linux kernel more than 6 years. The original C group code was contributed by Google. They've been using it in production at scale for quite some time. Containers are mature technology. But when we say the word container, that means something different to a lot of people. And I'm going to give you all a definition, my personal definition of what a container is in today's world. It used to be, when we would say container, what we meant was a C group. And then we had other things that we would, like LXC, we would call that a container. So it's now some namespaces plus some C groups, we would call that a container. And then we had Docker come along, and Docker added this concept of the Docker image, which I'll talk about a little bit more. And all three of those things together is what makes a Docker container. So a C group plus a namespace plus an image, all three of those things together is what I call a container. So a C group is a way, it's a feature of the Linux kernel. It's a way for the kernel to group processes so that you can control how much of the system resources they can consume. So things like how much CPU they consume, how much memory they can allocate, how much disk I/O or network I/O they can do. And these can be arranged in a hierarchy. So you can have a C group that contains another C group. Then we have namespaces. So namespaces, again, another Linux kernel feature. And it gives you a restricted view of the system. So by default, when you log into a Linux system, you see what's called the root namespace. And the root namespace has everything attached to it already. So let's talk about the network namespace as an example. When you log into a machine, you're in the root namespace. If you run ifconfig to get a listing of all the addresses that are on that box, you're going to see the entire list. You're going to see VIFs, you're going to see bonding interfaces, you're going to see ETH0, ETH1, you're going to see all that stuff. And if you want to restrict that view so that a given container is only going to have access to maybe one of those, then when that namespace is cloned and restricted, it may only have just one thing in it. So when you do an ifconfig within a container that is running in a namespace in that way, you're going to see that limited view. And this applies to all sorts of things that the kernel does, right? So mounts, right? What file systems you have access to, like a chroot. So when you do clone new S, or when you use the chroot tool, what it's actually doing is calling clone new NS, and that's the most basic of the namespace features. There's one for UTS. This is like what happens as a result of running uname. So what the host name is when you ask for the host name. IPC deals with the interprocess communication, so things like semaphores. It would be really sucky if you had multiple machines on the same box and you created a semaphore and somebody in another container could access your semaphore. That would be really bad, so we've got namespaces for those too. We've also got a PID namespace. So the process ID list, when you enter a container, the first process is process ID 1. Instead of a init or systemd being process ID 1, it's whatever process you created inside the container. If you've created a PID namespace, you're going to get a process ID of 1, and each new that you create is going to increment up. We talked about the network one, and there's also a user namespace. Now, user namespace, as of the time I made these slides, was not supported in Docker yet, but the idea here is that you can have a user ID of whatever inside your container, and that can map to a user ID of something else outside the container. So you can do things like have user ID 0 inside the container so that you appear to be root, but that's actually mapping to a non-root user on the host system. And these can also be nested. So let's talk about Docker images. So a Docker image is definitely not the same thing as a glance image. It's not the same thing as a virtual hard drive or a virtual machine image. It is essentially a tar file with some additional metadata in it. And these things have a hierarchy, meaning that an image that is at the very root of the hierarchy is called a base image. And you can actually create your own from scratch if you want, like an empty one, and you can put your own stuff in it. That's one way to do containers. But another way to do it is when you define your container, when you're going to build the container image, you say this image is from another image that has a name. So I might have a named base image called Ubuntu. Ubuntu : latest might be one that's available in my container registry. And so if I create a new container that is from that, I am now creating this hierarchy. And so my container has only got the bits that are unique to my application or whatever modifications are in my container, but nothing relating to what's in Ubuntu. So container images end up being very, very small by comparison to virtual machine images. The Docker registry is just like a Git repository. How many of you use Git every single day in your work? Okay, 90% of the room. So you all know the semantics of a Git repo. You pull or you clone, right, in order to get your code out of the repo. If you make a change and you want to save it, you do a commit. When you're done with the commit, you do a push in order to put it back up into the registry. All those same commands work with Docker. So if you understand Git, the Docker registry is just like a Git repo, but the things that you're putting in it are these binary container images instead. So all of you totally understand this already. So let's review. A container is three things. It's the C group plus the namespaces plus the Docker image, and that's what gives you the container. So let's talk about the Docker file. The Docker file is not the same thing as a Docker image. A Docker file is basically like a make file. So in the case of a make file, you're starting with C source code and this make file that says how it gets compiled, basically a script. And then when you're done, you get a binary output, right? With a Docker file, you have some directory full of stuff, and you've got this Docker file, basically the script, and you run Docker build against that Docker file, and you produce a container image. That's the binary output. So essentially it's the same thing as a make file, except the things that go in are a directory full of stuff and some commands that might run on the container. And then what you get out the back is the container image. And we'll actually see this today. We'll actually be making container images. So this is what a Docker file looks like. This one says, I am extending from CentOS version 6. The from line is required unless you are a base image, okay? So in the general case, when you're making Docker images, especially when you're a novice, you're always going to have a from line, okay? Maintainer line is just a way to label this Docker file to say who's taking care of it. It's totally optional. A run command says, while I am building the image in the context of the container, so any process that is in the container, run this command. So in this case, I start with CentOS and I install SSH in that container. I expose port 22, which means when I run this container, I can map port 22 of this container to another port on the host. I'm adding a file called start.sh, which would come from the current directory where I'm running Docker build, and it would put it into the container at the location /start.sh. And when this container runs, it's going to run the thing that's on the CMD line. So there's a difference between the run line and the CMD line. So run happens only during the container build process. Once you have the container image, that never runs again. And CMD runs every single time you start the container. So this just takes my start script and runs it. Now let's say I did that and I said, save my container image as something called Adrian server with SSH. Okay, so I started with this one, and I saved a Docker container called Adrian server with SSH. Now I'm making another Docker file that is going to extend that. So this is the grandchild image in this case. And so I say, all right, I've already got the SSH server here. I'm going to install the Apache server. And instead of exposing just 22, I'm going to expose 22 and 80. And again, I'm going to put another start script in. So it's going to overwrite the first start script with the one that I put in the second time. So this is a way so that you can have your base operating system is just taken care of by whatever upstream you picked. Okay? Your stack for running whatever your app is handled in this middle tier. And then your app that runs on that stack is the grandchild. So what you actually ship, if you do this grandchild approach, is going to be really, really small, because it's just going to be the files that are related to your app. It won't be the whole app stack, and it won't be the operating system. That stuff will just be there already, and you're going to use it again and again for all the different apps that you deploy that are using a common from line. Docker containers have a life cycle, and kind of like we do, where when you're conceived, right, we have a build. So when you create a Docker image from a Docker file, that's the birth or the conception of a container. You can bring it to life by doing run, which is a combination of two things. Run is a create and a start. So you could individually do container create, which says make the place in the kernel where these things are going to be started, but don't actually start any processes yet. Just make the namespaces in the C group and use this Docker image to set up the file system for it. And then you can start it at a later time. Then there's reproduction. You could, just like you can with source code, right? You can commit, and once you've commit, you could push it back up to the registry, go to another host and run it, or you could just run it again as a modified image. I would argue that it's generally not a good idea. I wouldn't recommend using commit. It's better if all of your containers just come from Docker files rather than coming from some manually driven process where you did something one-off, not from some automated formula. It's not a best practice, but you can if you need to, okay? There's sleep. You can either stop the processes by using a Docker stop command, or you can actually kill off all the processes in the container and then start them up again later, which is much, much faster than creating a whole new container. Then there's wake. You could start ones that are stopped. There's death, which you can do an RM on a container. So if you have a container and you've killed the processes inside of it, you can do an RM, which says take away the namespaces and take away the C group and take away the file system, just discard everything. And then there's extinction, right? Extinction is, I don't care about the image that I used to create this container to begin with. Get rid of that too. So if you've gone through all the way through kill and RM and RMI, you are back to a nothing state again. All right, now as of the time I wrote these slides, which was maybe 6 months ago, this was version 1.4. These are the different commands that the Docker CLI can do. I bolded the ones that you're probably going to use a lot. We're going to actually do a hands-on here, so I'm not going to explain what everyone does. But if you just run Docker with no command line argument, you're going to get this list. So in the Docker world, containers all share the same kernel. But you don't necessarily need to run the same OS environment. Or when I say OS, I mean like system library environment. You can run different ones in different containers on the same host, because the Linux kernels are all compatible, right? The Linux distro is only dependent on the kernel. It's not dependent on anything else running next to it. So you can run a single kernel with, here I've got an Ubuntu environment. I'll demo this too for you later. I've got an Ubuntu environment sitting next to a CentOS environment, sitting next to a Debian environment, and all on the same host running the same kernel. If you want to run, say, a web server, this is a web server that's going to be listening on HTTP and HTTPS ports, use Docker run. -D is for running as a background daemon. P is a port mapping. The thing that comes first, this is 80:80. So it says, on the host, port number 80, run what's happening in the container on port 80. But I might say, oh, on the host, I really want it to be 8,000, in which case this would be 8000:80. And then -P, run port 443 from the container on port 443 of the host, and run the container from the image httpd:/latest. And I don't have a command at the end here. So that means it's going to run whatever is specified on the CMD line of the Docker file that was used to build this container. So whatever the default command is what's going to run. You're also able to inject environment variables at the time that you create the container that will be available to all the processes that start in that container. So the -E here, so I've got Docker run, I've named it DB, so I can refer to this container later as DB. I've mapped port 3306 from the inside to outside, and I've said -E, the MySQL root password is this, and I've also said -V. So -V is a volume mount, or also referred to as a bind mount, where the file system belonging to the host is made available to what's running inside the container. So by default, containers have their own file system that's layered on top of the host file system. And if you don't want that, and you want things that you read and write to actually be happening down at the host, this is how you do it. So I might say everything under var_lib_html, or say var_lib_html, I want to be bind mounted to the host. Or I'm going to run a MySQL container, so var_lib_mysql, I want to be mapped to some volume that I have mounted on the host. And that way I'm not actually putting files into the container file system, I'm putting them onto a host file system. So let's use it. Actually, hold on. This is toolbox overview. So I haven't talked about the different tools in the Docker ecosystem. We'll do that first, and then we'll actually touch it. So Docker Hub, this is where the base images all come from. This is a service hosted by Docker. Docker Inc. So I didn't explain. So Docker is an open source project, and it's also a company. The company used to be called DocCloud and is now called Docker Inc. So Docker Inc. hosts a registry for Docker, the open source project, to use as the upstream for where your base images come from. They also sell private repositories, meaning you need a username and password login in order to access the images. And this is a way that Docker Inc. can make money. And if you want to change or view what's in there, you need to be properly authenticated either using their credentials or from a GitHub credentials. That's SSO with GitHub as well. Docker also has something called a trusted build system. This essentially takes code that you put on GitHub and looks for a Docker file in the repo. So if your source repo has a Docker file in it, it will, every time you do a commit, it's going to get a trigger. It will check out that code and build a container for the Docker file. So you can always have the current container that goes with whatever code is in a code repo if you're using this system. CoreOS is a micro OS, meaning it's got just enough to run Docker, SSH, etcd, and systemd. That's it. So it's like a little tiny mini operating system that's good for nothing but starting up containers, essentially. Okay? The CoreOS has another software called Fleet that you use to make a cluster of CoreOS nodes, which then you can distribute work onto. And this is suitable if you're running microservices. And you can set the hosts to automatically update themselves so that you're always running the most current version of code. If you decide to use that option, that can be tricky if you're running pets. pets are hosts that have names that you care about if they die, rather than running cattle. So if you're running cattle, if a single node reboots because it's restarting to add new code, you just don't care. So if you can afford to do that deployment model, this can be really handy because it can save a lot of ops effort in keeping your hosts up to date. Okay, Weave and Flannel. Both of these tools are what we refer to as overlay networks. They both use either UDP tunnels or VXLAN in order to make essentially like a VPN connection between the containers themselves. Weave is basically a shell script wrapper around a whole bunch of Linux networking commands that make it convenient to set up a peer-to-peer network. One of the cool things that Weave does is if you have, say, location A, location B, and location C, and location B goes down, or you can just like alternately route. Like if the link between A and B goes down and you still want to reach it, it could go through the other way. So it's a little bit more than just tunnels between hosts. There's actually some auto-discovery about where the nodes are, a little bit of routing in there. Flannel is another one. It's a functional equivalent to Weave. It's a little bit easier to get going in terms of the install. Well, I don't know. They're both pretty easy to use. They're both pretty easy to get set up. But Flannel is the one from the CoreOS community, and Weave is another one that's been around maybe a little longer. And we have some examples on using Weave here later in the course. So this is an expression of what you can do with Flannel. You can see there's both routing and tunneling going on here. There's Kubernetes. I talked about this a little bit earlier today in the morning keynote. Kubernetes is a project that Google started, taking the lessons learned from many years of operating containers at scale. Kubernetes is the way that Google wants to share how this should be done with the outside world. So they're taking their opinionated view and making that available as an open source project. They went around at the time of launching this to get community participation, and they've got a surprisingly active community contributing to that project. It is essentially an orchestration system that uses a concept called a pod. A pod is a grouping of containers that are expected to run together on the same host. And if you're using a microservices design, some of your services need to interact with each other at high speed, or may even need to share resources that are on the same host. Like a logger, you really want to stream the log stream directly to the logger right there next to the app where it's being created. And maybe the logger's job is to send that off over syslog or to a network service where you use to aggregate logs, that kind of thing. That's a perfect example. You might have a queue service. Maybe your application is extremely sensitive to latency, and you don't want any latency between the app and the queue service, so having them on the same host allows your app to perform better. That's another reason why you would group them in the same pod, that sort of thing. Most of the things that people want to do with containers can be accomplished by Kubernetes, but it is a declarative system, which means you describe the intended end state in the form of a YAML file, and you give that to the Kubernetes service through an API call, and it goes off and gets it done. And you don't care about the details of how it gets done, you just want it to happen. But if you do care about the process, you need to use something else that is more imperative in nature, where you can actually say, yeah, hey, in step 3, we're going to do this different thing instead. Kubernetes isn't going to give you that level of customization in what happens in the orchestration process. The way that it works is the nodes where the containers are going to run are called minions, and they report up to this thing called the master. So there's essentially a centralized control that has the cluster state in it. That's the master. That's the thing that's going to accept your requests to make containers show up on hosts. And then the containers are actually going to be run on the minions. So it's kind of like a queue and workers. So the minions are like the workers, and the master's like the queue. Okay. So let's talk about all the ways that Docker works with OpenStack. This morning I mentioned Nova Docker. This is a virt driver for Nova, so that when you ask Nova for a an instance, instead of getting a virtual machine or a bare metal instance, you're actually going to get a container out of Nova that's going to be running on the compute host. There's also a heat resource so that you can create essentially a Nova instance that has containers on top of it, and you can represent them in the heat DSL. So in the hot format, which is the format of the template that we feed into the heat service, you can actually have containers that depend on clouds, or that depend on Nova instances. So you can do things in orchestration so that containers show up in the process of running your orchestration. The trouble is that the heat resource as a standalone thing isn't as useful as something like a Kubernetes because there's no scheduler. There's no like container management logic. There's no placement logic. There's nothing like that. It's just create a container on a specified instance. Then there's Magnum. Magnum is for cloud operators who want to offer containers as a service, and it's integrated with Keystone so that you use the same authentication credentials that you use to create cloud resources like Nova instances and Cinder volumes and storage volumes. You also use to create containers. All right, so let's get to the hands-on stuff. So anybody not have the Docker, the slides? Everybody have slides, right? Yes. Okay, everybody have the Docker client and the Docker machine binary? Yes? Okay, anybody not have that stuff and need help getting it going? Okay, if you don't have that stuff and you need to get it going, one of our guys will help you get that done, okay?
I think a lot of people must be running it. If you go look at the help for Docker machine, when it says OSX and Linux, it actually pulls down a Darwin binary that won't run on your Linux pod. So that's what I ran into, and I just followed the help there.
Okay. Simon can probably help you through that, or Andrew can help you through that as well. All right, so in preparation for running these tools, you need to set some environment variables in your shell. The first thing you need is to specify what region your resources are going to be created in. So this depends, what this value is depends on what your cloud has. If you're using the Rackspace cloud, I recommend you use IAD. That's going to have the most available capacity for all of us. You need to specify your username and your API key. If you're using a Rackspace Cloud Account and you don't know where to get your API key, raise your hand. Okay, great. This one? Got it? Okay. All right. So everybody got their environment variables set, yes? Yes, 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 yes. Okay. So the first thing we're going to do is create a Docker host using a Docker machine command. What this is going to do, in fact, I'll do it with you. Okay, we'll use Docker machine create -d Rackspace machine 1. Are you all able to see that? It's probably huge, yeah. So Docker Machine is a tool for creating a host that runs a Docker daemon. And what we're going to do, instead of running Docker on all of our local laptops, because if we did that and we start doing like descends from Ubuntu or descends from CentOS, I'm going to have 66 people downloading the operating system and nothing is going to get done, okay? So please don't do that. Instead, what we're going to do is you're going to use Docker Machine to create a Nova instance in your cloud, and then we're going to run Docker on that. So when we pull down images from the Docker registry, or from the Docker registry, it's going to pull over the data center links instead of pulling over our Wi-Fi link here. And hopefully, that keeps us all going, all right? I'll make no apologies for the quality or bandwidth of the network. So these are the things Docker Machine can do. It uses create in order to make a new one. Like I mentioned before, in my examples, if I've got the word Rackspace and you're not using a Rackspace account, you just put the word OpenStack there instead. There are a bunch of different drivers. There's one for just about every kind of virtualization there is. There's one for VirtualBox. There's one for OpenStack. There's one for Rackspace Cloud. There's one for Google Cloud. There's one for VMware, both vCloud and vCloud Air. There's one for SoftLayer, DigitalOcean. You get the idea. So all the different kinds of places you might be able to start a machine in the cloud, Docker Machine knows how to do that. And it will install the latest version of the Docker daemon on the host that you create. And then from that point, you're going to use your local Docker client on all your laptops to communicate over an SSH tunnel to that remote machine initially. And then you're going to use a TLS connection between your local client and the version running in the cloud. So let's do it. Machine 1. So let me explain what this is doing. This should take about 1.5 minutes on Rackspace, depending on the speed of your cloud, plus or minus a few minutes. What it does first is it says to the Nova API that you've set up your environment variables to interact with, it says, give me a Nova server, or a Nova instance. Once it gets the IP of that instance and the status goes to ready, it will then make an SSH connection using the key pair. When it creates a Nova server, it creates it with a key pair argument. So it injects an SSH key into the host. It uses that SSH key to connect to the host. Then it runs a sequence of commands to get the Docker daemon installed. Then it creates a TLS key pair. The TLS key pair, the private key goes on your laptop. The public key goes on the remote server, and so there's a trust setup. So your interactions that are going over the API to the Docker daemon are all being tunneled through TLS so that only your commands are going to be accepted by the API. Any random guy on the internet is not going to be able to just start processes on your machine through your Docker client, okay? It doesn't. We did use CoreOS by default. No, we used Ubuntu by default. It does work on CoreOS. It does work on Ubuntu. It should work on most of the upstream OSs. But all it really does is it makes a connection to the Docker web server and downloads the client and installs the package based on the auto-detected OS type. So it should work on other OSs, but I know it works on Ubuntu. So if you're deciding what image to use, then use the image ID that goes with Ubuntu. All right, so mine finished. Anyone else finish? Okay, I got maybe 10% of the room done, so we'll hang out for a little while before we move past this point.
So the minus B, I can use DigitalOcean?
Yes, you can use DigitalOcean. You can use any of the drivers. It really doesn't matter. I mean, I titled this talk using Docker with OpenStack. Right. But yeah, for the purposes of this session, if you've got credentials on any cloud, all of this should work equally well. Yeah. So DigitalOcean, SoftLayer, EC2, pretty much anything.
What if I had a pack stack all-in-one virtual machine running on my local box? Would this work?
Yes, you can do that too. As long as you're not, well, Yes, but then when you go to actually run the Docker container, it's going to download the image. So your start time,
The advantage of having the,
yeah, your start time is going to be dependent on our local network here if you do it that way. Maybe it'll be okay, but it's.
but if I want to go back and try this out,
Yeah. You can use. There's a VirtualBox driver too. A lot of us are running that, and so that works the same way as this. I would just do -d VirtualBox, and it would put it on the local boot to Docker.
or KVM or something.
Exactly, or KVM, exactly.
So now it's actually in the background, I can see in my Rackspace account, it's starting these two machines. And what OS is running that? You said it's CoreOS, or, I mean, how is that?
It runs CoreOS on the machine, or actually it runs Ubuntu on the machine.
Okay, so how did you decide that it needs to do Core Ubuntu?
It just has a default value for the glance ID in the client. So when you're using the OpenStack one, you can actually specify what glance ID it uses. That's how, yeah.
But if you just do create a machine, it'll by default just pick Ubuntu.
Yes. Well, it'll pick a UUID value, which you're not likely to, well, it'll pick a UUID. If you're using the Rackspace driver, it's going to pick a UUID value that we already have in our public catalog. Does that make sense? It'll be in our public glance catalog. Yeah, so it'll be available to everyone. All right, so how many are up with at least one machine so far? More hands? One more? Okay.
Does the image have to have anything specific pre-baked in it, or the Docker to know what to do?
Curl. It has to have curl on it.
Predefined user?
No. No, because it injects the host key as a root key. Yeah. All right, so my second one finished. Take notice of this little command that it gives you when it finishes the Docker machine create. It gives you this little eval command. And what that does is it sets the environment variables. Let's just run this like this, hold on. See those three environment variables? That's what it sets. So I just say, do that. So this is telling it that it's going to be doing TLS to communicate with the remote server, where to find the remote server, and where my local certificate is that it generated for me. So if I do an LS, if I do a Docker machine LS, what it's going to do is look at my list of servers. Well, there's some latency. All right, and you see there's two machines that I've created here, machine 1 and machine 2. And machine 2 is the active machine. So if I run Docker commands right now, they're not going to run on my local box. They're going to run on machine 2. So if I run Docker PS, I should see no containers running, right? PS minus A, that's a list of all containers ever created, not deleted. Again, I should get an empty list. Minus I minus T means interactive with a TTY. You can also put these together like that. What image you want to run. And this does not matter, right? You can pick here whether you want to run it on Debian, Ubuntu, BusyBox, I don't care. You can pick whatever Docker image tag you want here. And then what command you want to run if you don't want to run whatever was default. So this has made an API connection to the remote server and told Docker to run bash on a CentOS box. So right now it's pulling down the CentOS image. And now I'm on the remote box. So if I run uname, it's like IRC in 1993. You'll see here I'm running on an Ubuntu kernel. And if I exit this container and I run, you see this is my Mac. Okay, and the second time I run that, you'll notice it comes back a bit quicker because it's already got the CentOS image on it. It didn't have to download it the second time, right? Now let's say this time, instead of running CentOS 6, I wanted to run CentOS 7. It would download the bits that are different between CentOS 6 and CentOS 7. Since CentOS 7 is actually a descendant or a derivative of CentOS 6. So it says I'm downloading only 77 megabytes here instead of the few hundred megabytes that I would expect this to be. All right, now I'm running Red Hat, version 7. Let's say I only wanted to run Ubuntu here, or let's say Debian. You get the idea. Let's go back to the lab here. So all the containers I've run so far have all been interactive. So when I exit them, the containers are stopping, but they are not being removed. So if I do, at the end of this Debian being created, if I do a Docker PS, so this is a Debian box, also same kernel again, right? Same Ubuntu kernel, but now I'm running a Debian distro on top of it. So Docker PS shows me the list of running containers. There are none. Docker PS minus A shows me all the containers I've created. I should get a list of 4 of them that I created. Let's say I want to run this same one again, this Debian one. I say, oh, I like the CentOS 6 one again. I might say Docker start that one. Now I can do an attach. Because I did it twice in a row to show you first I downloaded it from, to show you that it would download the CentOS 6 image. And the second time I ran it just the same thing again to show you it doesn't do that the second time.
Oh, so the minute you run a command on an image, it'll show up here.
Yeah. So you see here I'm reattached to this same bash again. Now I'm back in. I'm back in 6.6 again. So you get the idea. You can start up containers that have been stopped. Now let's say I don't want to do, I don't want to use this container anymore, and I want it to go away. I would do docker rm, and you can actually remove more than one at a time, you just list them all out like this. And now I'm telling the remote API, go ahead and delete all those containers. So now I run a PS against it again, and I'm going to get an empty list. So that's how you clean up after yourself. I didn't show you. Okay, Docker machine has a IP address. You can get by running IP. You can also connect to it, just like with Vagrant. You can do a Vagrant SSH and you get into the box. Docker machine has that too. It's the functional equivalent to Vagrant. If I want to make the active machine 1 instead of machine 2, that'll log me into machine 1 instead. You get the idea. So you can, by toggling active, you can decide which of them you're going to talk to at a given time. Okay. So early on, when Docker was new, here, let me just talk to this slide for a little bit. When Docker was new, in order to get into a container, you had to either know that you could run NSEnter in order to create a process in the container. Or what a lot of people were doing is they were actually running SSHDs inside of containers and using an SSH client in order to SSH into the container. Don't do that. That just causes a whole bunch more SSHD servers that don't need to be there. Instead, you're already running an SSH service on the host, okay? You can create a shell anytime you want in any of your containers from the host by using something called Docker exec. So Docker exec -i, which for interactive, -t for I want a TTY. Sometimes the things you run, you actually don't want a TTY, which is why these flags are here. The name of the machine, this should say machine 2, and then the name of the command you want to run. So in this case, if what I really want is, let's start, so set active to machine 2, go back and create my machine again. Okay. So let's just do that as a background. So if I say -d, it's instead of going to be running in the foreground, it's going to be running in the background. And I'm going to say, instead of running bash, I'm going to run sleep for 30 days. Okay, so now I've got a container that's running, right? Docker ps just shows me that machine. I can say Docker exec -i -t, this container ID. By the way, you don't need to use the full hash of the container. You only need enough of it so that it's unique. So in this case, I could probably call it 0a, and that'll probably be enough. And then the command I want to run.
Also, I can also use that funny name, right? Yes.
Yeah, you can use this auto-assigned name. So every Docker command, when you identify the container that you're running, can either be the ID or the name. And you can specify the name when you start it, right? So if you say, I want to run, oh, I shouldn't have removed that. Hold on. Okay, where was I? I was showing you that you can name a let's call it foo, okay? The image, and then and then the command name. All right. So you don't have to run SSH in the container. You can just create a process, whatever process you want in whatever container you want, just by using exec. There's another way to use a tool called NSEnter, which gives you more control over the kind of namespace that you create. And this is useful if you want to only share some of the namespaces, but not all of them. Like, so say you want to create a process that shares the network namespace, but not the PID namespace. Or you want to create one that shares the, anyway, you get the idea. You can do creative groupings of new processes that you start across your different containers and control what namespaces your new processes share or don't. All right, so moving a Docker image to another host requires that you have a repository that you can write to. So using Docker Hub, you can, if you don't already have a Docker Hub account, you can create one there. It takes a minute. You can log in. Once you've got an account on Docker Hub, you run this command docker login. And docker login authenticates you against your account so that when you do a commit, now you can do a push. You can tag it with a name and then do a push into the private repository so that you can check it out on another machine. So we've got our two machines here. You can actually do make a change in one of the containers, do a commit, do a push, and then run the command using the resulting repository name after you do a Docker login on the second host. And now you can run the same container with the same state that you committed on host 1. So it's a way of doing migration, essentially using an export and import process.
Good question.
Yeah,
So that's a warm migration.
it's a cold migration. Well, I don't know.
Yeah.
You might call it warm, but I would call it, it's really export, import, not a migration.
Okay.
Yeah.
So I actually have two observations. One on the previous lab. So we run our Docker containers as part of our testing process. And what we realized is the tip actually for everything. They don't do Docker run or Docker exec. That's T-I, because Jenkins has its own PTY. So if you do that, it actually is a non-blocking step in Jenkins. If you just Docker exec, then we want the Docker container with the command that we want.
Exactly.
It's a blocking process for your Jenkins job. The other observation that we have is that we can actually, so what you're doing is one registry that you're actually committing to that registry, stopping it, starting it again on a different machine.
Right.
What we've also observed over a period of time is that you can actually do it across two different registries as well. If you do a Docker save and a Docker load. So Docker save can save your image as a tarball.
Right.
Tarball.
Yeah, Docker save and Docker export, I think, are aliases. And that just takes the contents of the image and gives it to you as a tar stream, which you can save into a tar file. And then you could, without a registry at all, you could just copy the tar file to somewhere else and start it back up. Or yes, you could put it into another registry. Right.
The difference that we've observed is that if you do a Docker export and an import, it doesn't get the metadata that is.
That's right. It flattens all the layers.
So when you do a Docker import and try to start the container, it has no notion for what your command was or what your entry point was.
That's right. That's right. It's generally better just to build to start always from a Docker file and build, rather than modifying an image and expecting to be able to move that around.
Also, the problem that we were trying to address was that the Docker system, if we wanted to start a container, it was a firewall inline system,
Mhm.
so it had no access to offsite work.
Okay.
We wanted to do like OpenStack.
Right. But you can import images from TARs.
Yeah, so that's what we did.
Yeah.
We built the image first, and then with our own, with the
Yeah, that works. That works. All right, so in the interest of time, I'm not going to demonstrate this, but I'll leave this in your capable hands of doing this. The key here is just the Docker login. You do the Docker login on each host where you want to be able to push or pull from your private repo. Does anybody need a break? No, we're all good. Okay, lesson 2. Yes.
You showed the Docker machine EMV that you sourced to toggle between the, I also saw you doing Docker active.
Oh, active is how you change by default. If you don't specify the machine name, which of the Docker machines you're going to be interacting with when you run Docker machine IP or when you run Docker machine SSH. So if I run Docker machine SSH machine 1, I'm going to get machine 1. If I run Docker machine SSH machine 2, I'm going to get machine 2. If I just run Docker machine SSH, I'm going to get whatever was marked as active.
So is that all it works for? It doesn't toggle you for the actual Docker command then?
It actually does. When you switch from one to another, it actually does.
I tried it. It wasn't switching.
Actually, it depends on the version of the client that you're using. But the best practice there is to set it every time. If you want to change, like, you either specify everything explicitly, or you set it every time. That's the best way to do it. It's going to work across any client, regardless of the version of it. Yeah. Time's up. Yes.
When you say Docker commit, and you put 1, right? So what is that 1 map to? Because when I tried, it said it doesn't know such ID. So what ID is it actually?
Docker commit. Which one?
Yeah, no. Please go forward. Next one. So,
Oh, ONE. In this case, is actually machine 1.
so I should put machine 1 there.
See right here, machine. This is actually this is a bug in my slide. That should say machine 1. Or actually, hold on a sec. No, I take it back. This says commit the container named 1, because we created earlier on. We created 1 and 2. So Docker. So we got a container named 1. We got a container named 2. I say. So sorry, it's not a bug. It's actually right. Docker commit the container 1, right? The state of that one to the path of the private repository with a tag on the end, right? Okay. So Docker files, this is what I showed you earlier. From maintainer, run, expose, add, and CMD. Remember, run only happens when you build the image, and CMD only happens when you run the image. So from is either in the format name or name:tag. If you don't specify a :tag, it's going to use :latest by default. The maintainer line is optional. The run command is going to run at the time that you build. The expose command is if you ran, okay, so there's this flag for Docker called -P. And how that works is when you use -P, it will automatically pick what was on the expose line and map it to a random port on the host, so that you get a random port on the host that maps to whatever you exposed. So if you're using a system like a Kubernetes, where it's got a services capability that's going to connect you to it, it doesn't want to take care of static mapping. It just creates it on the fly. Whatever Docker applies, it's going to connect the service up to that port. So if you were doing this in an orchestration system, -P makes a whole lot of sense. If you're creating these things explicitly, lowercase p, and specifying the actual port mapping of what you want externally and what you want internally makes more sense. So it just depends on what you're trying to do. Add is for adding files. You put the source file first, that's the local one that's in the build directory, and then the destination is where you want it to land inside the container. All right. So this is how Docker files are built. You make a new directory, you go into it, you put a file in there called Docker file. You put in your Docker file language, right? The from, maintainer, add, any CMDs, or any runs you want, and then your CMD line and your expose line. And you save that, and then you run docker build -t, the name of the image you want to create, and any tag that you want to attach to it. You want to see how to copy? How much time do I have here? All right, so we got half an hour, a little less than half an hour left. So let's do a little bit of Docker copying. Okay, so CP. So in CP, you specify the name of the container or the ID of the container, and then a colon and a path of the thing that you want to, sorry, a thing that you want to copy. And then a path to a place where you want to put it. So now my Mac has that file on it. And this is handy, like if I'm in the process of building, experimenting with some containers, and I've made a configuration, like of a Galera cluster maybe, like I've done this recently, where I wanted the configuration of the one Galera node, and I wanted to put the exact same config on another node, I would actually use Docker copy to copy the file out to be sure that I had exactly the same version of the file on both of the environments that I was testing with. But you can also do the reverse of this. So using a bind mount -v. So let's say this temp directory I want to mount to /Adrian inside the container, okay? Cannot stat. Okay, hold on. Thank you, yeah. Thank you. See, I brought my experts with me. Keep me straight. All right, so now I had machine one. Oh, I think I was working on machine one, right?
So it mounted your local machines temp to the remotes?
No, it mapped the hosts / temp to the containers / Adrian. So I'm going to get into the host and I'm just going to show you how this works. Okay, so I'm on machine one and I'm on a container on machine one. Let's put this side by side here. Let me make this a little smaller. So there's the host. And there's the container. I can't spell my name. Okay, so I'm in /Adrian in the container on the right. I'm in machine one /temp on the left. See how that works? So the host and the container are in sync in terms of their file systems because I'm not using the container file system, I'm using the host file system. Okay. So that's how you get things from the host in, right? I would put something in /temp and then I would copy it. So I created this hi.text came from the host, right? That's where I created it. I could just do cp that to. Now it's in the container, right? You get the idea.
So the Docker CP isn't symmetrical? You can't go in or out?
No, Docker CP is only for slurping stuff out of the container. It's not for putting it back. I don't know why, but that's the way it works, yeah. Okay, so we talked about Docker commit. I mentioned before doing commit and creating new images is something you can do. I think that's fine if you're just playing around with stuff. It's not fine in a production environment where you want your environment to be repeatable. In that case, the best practice is create your images from a Docker build, from a Docker file, not by creating an image like I've been doing here in these demonstrations, fooling around with them, getting them to like a golden image, and then doing a commit on them and pushing them up. That's generally a bad idea. If you have a Docker file, you have a way to create the image the same way every time, repeatedly. And that's what I would recommend. And I would recommend putting the Docker file, if it's for an app, I would put the Docker file right in the code repo with the source code. So I made a Git repository that has a demo Docker file in it, like the ones I've been showing you. So you can clone this repo, github.com/adrianotto/dockerfile_demo. And it has a couple of things in it. Yeah, you can, well, wherever you want to clone it. I don't care. Wherever you want to do your Docker build. but I would do it on my laptop. If you're having trouble with the network, you might actually want to do it remotely. I've seen the network's pretty laggy right now. But I'm going to show you what's in that. Okay, you can see that, yeah? Okay. So there are 4 files in here. I've got a Docker file. This says from CentOS, maintainer is my name. You can put whatever you want on the maintainer line. It doesn't have to be an email address. I do a yum update, and then I do a yum install of Apache, and then I add the start script that I created, and I expose port 80, and then I make my command to run my start script. So the start script, because a container has no init process, if you use like initd scripts, they will not be started when the container is started. The only things that are going to start when your container starts are the things that you explicitly start. So what I do in the way I use Docker is I always just have a script like this, and I start up my stuff from my script. And that way, if I want to start services, I can. I just use service whatever start in my start script. And then at the end, I sleep indefinitely. And that way, the container doesn't go away when I'm done starting my services. It stays around. But the thing that it's actually running is actually doing nothing. And that way, I can do a Docker attach, or I can do a Docker exec to get a shell in this container later if I want to. And I'm going to be able to go in there and start more processes or do whatever I want.
So that means your start.sh gets bit number 1?
Yeah, exactly. You don't have to do it this way. There are different ways to do this. Another way to do it is you just have your app put something onto standard out and not exit. Like a -d. You can run your app with a -d, so that it's holding standard out open, and then you're going to be able to get that output from Docker logs.
So we figured out that on CentOS 6 you can also do /sbin init as part of your command.
You could.
And then you can run any.
You can also run system, well, depending on whether you run it privileged or not, you can actually run systemd inside of a privileged container.
With this, when you do a Docker kill, how's that going to handle the sig term that it says?
It's going to, okay, great question, Andrew. He asked, what happens when I do a Docker kill? What happens to all the processes that I create? If I have more than one process, it's in a C group. When you signal a C group, everything in that entire PID hierarchy gets the same signal. So if I send a sig term to a Docker container, all of the subprocesses in that PID tree are also going to get sig term. So it's a way to kill off all of your processes at once. It's actually really convenient because sometimes what I actually do want when I stop a service is for this entire grouping of processes all to end at the same time. In that case, I might actually put them all in the same container together like this, rather than having different containers for every single process. It's easier to deal with them all at once. Yeah. So what am I teaching you? I've lost track now. Oh, we were doing Docker files. Okay. So I also put a script in here called build.sh. Now, there is a tool called Docker Compose that allows you to do this in a more graceful way. This workshop was actually prepared before Docker Compose existed. So my apologies. It would have been cooler if I had time to update this, but I've been too busy, sorry. But you don't have to use Compose. You can use whatever the hell you want. So this is an example of a super simple shell script that just does a Docker build process. So I set a variable here. I get the date. I use the date as a tag. So when I build, I'm actually building httpd:/the date. I tag that against latest. And then I check to see, did my Docker tag command work? And if it did, then I kill off any other container that has the same name. I attach, which I expect this to fail, because you cannot attach to a container that has been killed. But if it takes a period of time for your processes to exit. There is a period of time where it's received the signal, but the processes aren't gone yet. Okay? And so what attach is going to do is it's going to block until all of those processes are actually gone. So Docker attach is my way of waiting before I start the new one for the old container to actually be gone. If I didn't do this and I just did Docker kill, Docker start, sometimes the Docker start won't actually run because there's another container still there because the processes have not stopped yet. Make sense? Okay. And then I run a new one and I give it a name and I say map port 80 on the host to 80 in the container, and I say run it in the background and run it from the image that I just built. And if that didn't work, then print a nice little error message. So let's try it. Okay. So now Docker build. So this is what a build looks like. Every stage of a build creates a new container. Every single one of those lines in your Docker file, unless it's at like the maintainer line, is going to do something. And that something does not happen on your host. It happens inside of the container that is created for the build process, that is intended to be around only for a temporary basis until the end of your build process, where we commit the container to an image. That's where the image actually comes from. It comes from the container that was running at the time the build was running. So this is doing the update. Question louder?
Where do the images actually live?
Where do the images actually live? At the time that you are building, the images live on the local varlib Docker directory using whatever storage driver you have chosen. So depending on who your upstream Linux provider is, that's going to determine what the storage backend is for this. I happen to be using it on CentOS, so it would be like the dev mapper backend. So you'd have like a virtual file that has metadata in it and another virtual file that has the actual data in it. So essentially, it's like having a Docker database for what's going on locally. Kind of like when you use Git, right? You get a local copy of the source. In the same way, you get a local copy, right? Remember I told you, if you understand Git, you understand repos? That's what's going on here. Okay. Exactly. There's no requirement that you use the Docker registry to store your stuff in it. You can just build your images wherever you want to use them if you want. I actually have production deployments of Docker that do not use a registry for any of my images. I only use the registry for the upstream stuff. So in some cases, I'm using production deployments where I started images from scratch. There's actually literally an image called scratch, and it is empty. There's nothing in it. So you can build your own Linux distro inside of the scratch image and then commit it, and that's your new base image, and then you can create your own Docker files against that. So you can have an entire environment that depends not at all on anything on the internet. Okay. So there's the container that I made. And if I do the same thing again, it's going to rebuild. Now here's an interesting thing. The Docker build process created those containers in the build process. Those containers are cached. So if I run the same build command again, the things that are the same will use the cached result instead of running again. So if I've changed my source code, of course it's going to be different. When I create the context, when you run Docker build, it basically like tars up everything that's in your directory and then feeds that into the Docker service as a stream. And it looks at the checksum of that data that you're checking in and determines if it's different. And if it is, then it actually does what the Docker file is asking it to. If nothing's different, it just uses whatever it's done before and doesn't repeat itself. So that's why Docker builds can be much faster when you repeat them. Why is this taking a long time? What's it doing? Oh, it's talking over our slow network. I know why, because I told you guys to do Docker build. And you know what Docker build is doing? It's flooding our network with activity. It's going to push the context up. So depending on what I told them to put in the context. This is only just a couple of text files, but still, it's whatever. Question here.
Is it possible to, if you have like a device driver, can you pass it to container to the?
If you have a device driver, can you pass it to the container?
Like
As a GPU resource, for example. You can give access to device files. Depending on what you want to do with that device, you might not have the rights. Because when you create a container, unless you create a privileged container, it drops the cap sysadmin capabilities. So you can't do things like mounting file systems. So the most common reason people want to do that is they've got like a file system on some device. Yes, you can get access to the device, but you can't actually mount it from inside the container after that. So you would need to use what's called privileged mode. So you create a privileged container. I think it's like dash privileged or something when you start the container, in which case it won't do the drop of the capabilities at the time that it starts it. It's a less secure way of running the container, but it allows you to do stuff like this. So yes, you could. Question there? 5 minutes? Okay. The question is, if I used Kilo today, how long would I need to wait for this to be just built into OpenStack? Well, everything I'm showing you today is possible with all OpenStack clouds. In terms of treating it as native from the Magnum perspective, Magnum is released. You can download it and use it today. If you're using it for experimental stuff, it's perfectly appropriate. I wouldn't recommend using it for mission critical workloads yet. You probably come back in the Liberty release time frame to see where we are at that point to decide whether you want to put serious stuff on it. Yeah, question? Okay. Okay, yeah, sorry about that. Okay. All right, so let's see if we did writing your own Docker file. I showed you the repo. I showed you the build script. I explained when you run things a second time that it uses a cached result. So if you have builds that are like 90% similar from one build to another build, put the thing that changes the most at the end of the Docker file, and you're going to speed up your build process a whole lot. Especially if you're doing stuff like yum update. Like in my example, I have a yum update command. That's not going to change 5 minutes from now when I rebuild my app, right? So it's great to put that at the top, and then to put like the add my source directory to somewhere in the container at the bottom. And that way, it's only changing the stuff that's actually changing, and my builds are much, much quicker than they would be the very first time. Okay. We got through all our material, and I've still got 3 minutes left. 2? Yeah, awesome. So I'll just take, we're done with the instruction half, or the lab half, the end. I'll take the rest of the time for questions, or we can just wrap up and you can come tackle me at the front. Thanks everyone for coming out.